Okay, then hello. So today we'll be briefly talking about TQFTs, and our approach will be we'll be talking them through spin systems, classical spin systems. Okay, so I will assume that you're familiar with some of the things. What I assume you're familiar with is assumed. So I will not explain those terminology. A little bit of module theory, algebra in general. I will assume you are familiar with representation theory a little bit, and category theory. Okay, and our roadmap will basically be as first we will talk about classical spin systems a bit to build the motivation for like why do we care about this stuff. So first we have classical spin systems, and then we will talk about axiomatic quantum, topological quantum field theory, which I will refer as TQFT. Then we will give the physical interpretation of these axioms. And then lastly, we'll try to express the Ising model, which I will explain in a second, as a TQFT. So there has been this mini lectures organized in the department where Dan Fried came, and then he talked about TQFTs and how to express Ising as that. So we'll be just focusing on a little part of his talk and then explaining all the things he said in a little bit more detail, and try to build an intuition behind it. Okay, so what are classical spin systems? Classical. So when physicists are usually trying to understand the many-body system, they often use classical spin systems. Well, I'll give examples, but first let's say what data we need to have a classical spin system. So first of all, we need to have spins, and then we need to know what values they can take. We need to know the values of spins. We need to know where they are, their locations. Where spins are. And then we need to know how they interact with each other, which is given by the energy associated to each configuration. Okay, so these three data will be enough for you to define a classical spin system. So one example will be to consider a magnet. A magnet. So you have a lattice. Okay, I'll tell about this, but okay, let me give an example. So maybe you have a lattice, and then you have little magnets here, and then they will try to align with each other, right? So that's just one of the most basic examples of classical spin system. So these have subsystems. So if the spins are sitting on a lattice, it's called a lattice spin system. If they're continuously distributed, it will be a field theory then. And then the energy associated with each configuration can also differ. For example, they might try to align with each other, and so that will be the case for a magnet. Or the system might have less energy if they are not aligned with each other. They're pointing in the opposite direction. So it differs. This is what your system is. So you might say, okay, you're talking about TQFTs, there's a quantum here, and then you're saying classical spin systems, like why? And then I will tell you that these systems can be quantized by taking a limit. So we're good enough to study classical spin systems now. So we need a toolkit to do measurements on the systems. So you can ask if there is a configuration n, what is the probability that your system will be in this configuration? And then this is given by, so this is an information we borrow from statistical mechanics. So this will be the weight of that configuration, so the energy at that configuration, times, so beta here is the inverse time. 1 divided by t. And then z here is to normalize everything, because you will have a weight for each configuration, and then to talk about probabilities, we need to normalize it. And then this function has a very specific name. It's called the partition function. So naturally, if we give these weights to every configuration, z will be given by the sum of each weight for every configuration. Okay, so until now it's I think good enough. But one of the problems people encounter is it's sometimes not that easy to calculate the partition function. So we have problems calculating this. So physicists have been trying to come up with ways to calculate this partition function. So this is what all this story is about, basically, to formulate the partition function nicely so we can understand it. And one of the approaches to calculate the partition function is a transfer matrix approach, which I want to explain through an example. Our aim will be basically to write such a matrix, such matrices, or in some cases, such that the partition function becomes the trace of, so for every point, so this product is over each point in your lattice or field, that will be just changing the product, but so you will have a series of matrices, and then the trace will give you the partition function to formulate the system in such matrices. And then explicitly write them, and then obviously try to calculate the trace. But anyways, okay. So let's give a basic example. And our example will be the Ising model. So the Ising model is not actually proposed by Ising. But anyways, he solved it in the first dimension as his PhD thesis, and thus it's named after him. So this is a model, a lattice model. So we have a lattice, right? We have a lattice, lovely. And then we have spins. So each spin can take the value of either positive or negative one. Okay, nice. So then if we have a lattice that has n points, lattice, then we will have 2 to the n possible configurations. Nice. And then we know what the values of spins are. Where the spins are, we assume there is a nice lattice, and then we need to know the energy associated to each configuration, and that will be given by, so suppose I give you that. The nth one, the spins have these values, I give you the step, and then you will have the energy as this. So the sum is over nearest neighbors. So let me have a look. So if you have a spin here, this can interact with this one, and that one. That's its nearest neighbors. That's what we assume for this model. And then, as you see, we just multiply them. So if they're the same, then it'll be a positive one. If they're different, then it'll come to negative, but then we have a negative because of the properties of the system. And then J here is just a couplet concept, but as we're doing mathematics, we're not going to care about this for today. Because this is not a physics talk. Anyway, so this is a little bit of hand-waving mathematics. So let's try to write this a bit more nicely, in the more generalized scheme, maybe. Okay. So we can view the values spins can take as a group, right? Because it's a physical model. Every state can evaluate another state and can change. So they must form a group. And then in the case of Ising, the group is just a group consisting of positive and negative one. Then we have a parameter beta. This is the inverse time. For model is fixed. It's a positive number. This is just inverse time.
It should be inverse temperature, no?
Oh, yes. Sorry. Yeah, thank you for correcting. Oh, okay, anyways. Yes, I wrote inverse temperature for some reason. Anyway. And then we have a weighting function, so this will take the values from the group, the values the spins can take, and then associate them to some number, a positive number, or what? Non-negative number. So in our case, in the case of Ising, this will be just taking to the e to the positive or negative beta. Okay, lovely. And then we need to have a configuration space, and then we'll denote this as S. I will tell what this is in a second. So then this is basically, in this case, just equal to A to the vertices of the lattice, which is actually just okay. So here, as we're trying to write in a more general form, can you see it?
The chair is blocking.
Oh, I can't move it away. Okay, lovely. So as we said, we're trying to write in the most general form, so we do not necessarily have to have a lattice like lying like this on space. So we can basically take any two manifold Y, and then we can stick a lattice on it. Right, so we can do this. So if we have something like this, for example, and then we can put a lattice on it. Nobody's gonna get mad for this. I don't know, maybe something like this. As long as it's defined, it'll be fine. Okay. So now, so this is the general case. So you can obviously change this. So you can say, okay, let me make my spins take other values, or maybe take the weight a little bit different, and then I'll give you another spin system. But we'll be mainly using this one as an example.
By a lattice, you just mean any graph or what?
Yes. Well, it's a graph that's stuck on, like, you stick it on the manifold. So you get points and edges.
Any graph, or you need some extra conditions?
Well,
About how partitions y into components or something.
okay, so if we want to do like very physical, yes, so it has to be a nice graph, like we would want the neighbors not to be like too distant from each other, like, because then the weights of their interaction might change, so that might cause problems. But in the most general case, it can be any graph, but that's not forbidden. Okay, and then in this case, you can ask, okay, with this formulation, what will our partition function be? And it will be this. So partition function will be, which is denoted by I from Ising over the manifold Y, and that is formula is the sum over each configuration possible. This is just this part, and then to form the weights. Oh, I also have one more function that I need to say. Bad use of area. Where should I write it? Okay, let me write it here. Okay, so we have one more function we need to say, which is g, and then g takes values from our configuration space, and then takes an edge and makes them go to A, an element of our group. What does this do? Well, this basically defines the ratio of boundary spins. And what we mean by this is, so we have a lattice, so we know the configuration, so we have this, and this G measures the difference of this two spins over that edge. Well, because we go over all edges, it will run through all of the nearest neighbor possibilities, right? Because we look at each edge, and then by using J, we can have our partition function, which will be, let me write it here, which will denote as I, and then this will be the sum over each configuration. And then to have the weights, we will have the weight function associating a weight to each ratio. And then this runs over all edges. Now, this part is actually just giving us the energy for each configuration. Same thing, formulated a little bit differently. That'll be useful. Where is this? And then as for the transfer matrix approach in this case, well, looking at this, there's a negative here, not a negative, okay. So looking at this, we can say if two are the same, if we have a matrix and then the two are the same, they're either positive or negative one, but has to be the same, then this will give us e to the positive beta, and then if they're different, this will give us e to the negative beta. So if you want to write this as a matrix, this will be something of this, like this. Too bad usage of variable, anyways. So positive beta on the angle and then negative beta on the other ones. But what's important is how to express the partition function in terms of this V matrix, and that will be.
So does this V matrix depend on the lattice? Like, are those basis states like
Yes.
nearest neighbors particularly, or? So like one like the left
Yes.
one is one site and then the other one is a neighboring site.
So yes, so they have to be true also because we take the sum over all nearest neighbors. So we're trying to express well through this, but then using this transfer matrix. So Zn in this case will be we take the sum. Okay, to be more precise, we can say like if they're not nearest neighbors, then it will give you 0. But anyways. Trying not to get into that part too much. I just want to say that it's possible to express it as a transfer matrix. And then there will be, I write a bit too big. So because of we're going over nearest neighbors, okay, let me here. And it will go like this. And because we're taking over the sum, these will all give us the identity. And what we're left with is, let me write it here, sorry for raising this, but I didn't want to raise anything. Here we are. So this will be, because this is important, the sum over this. Of how many spins there were, and then this is just the trace of Vn. Okay, so the point here is we can express the partition function as trace of a transfer matrix, So instead of dealing with all the physical stuff, we can write the transfer matrix and then try to calculate its trace.
What is Z n? Is it different from just Z, or why is it?
I denoted n here because it's the partition function for n points on the lattice. So there's n spins. It's not different. Here I just didn't note the number, so here there's a specific number. I wrote this to be able to write this and over here. Nothing different.
Sorry, n points on the lattice or n different spins?
So that's n points on the lattice.
Uh-huh.
So we're just trying to understand how they interact with each other. Okay, how we're going with time? Too bad. Anyways, okay, now this is what I more or less what I want to say about classical spin systems. Now moving forward to TQFTs. Okay, first a little remark. We're going to discuss what a boardism and a cobordism is. So, definition. We have the following data for a boardism. A boardism is, so we have a d-dimensional x. We split the boundary of x into two disjoint unions. So we have 0 and 1. And then we have two embeddings, theta 1 and theta 2. So this is the boardism, and we say it's from y0 to y1 if these guys so these are two embeddings. It takes y0 and then y1, but with reverse direction. So when we're trying to glue things, they will glue nicely. Such that we want the first one to go, let me say I, okay. To the first part of the boundary, and then the second one to go to the second part of the boundary. So if we want to draw this, I can draw it like this. So we have, this will be your x. It can have balls, whatever. Draw a little nicer. Okay, and then we split the boundary into two. It can also be like this. Right? Okay. So let's say this is the first part. And then this is the second part. So we want theta 1 to embed y0 here and y1 here. So just sticks. So then x becomes a higher dimensional manifold between these two manifolds. So here, these are, so if x is of dimension d, then y's are obviously of dimension d minus 1. So now we can tell me, so you wrote cobordism to what's a cobordism. So in the order literature, this was referred to as cobordism, but now they're used as the same word. So Dan Fried used boardism in this sense. So when in his lectures he always uses boardism. A little note too. So Atiyah has a paper called Boardism and Cobordism, and he uses these two words as different things. So he has a paper in the 60s, 1960, very precisely. So if you want to look at how he uses them, you can check that paper. He uses cobordism for this, but nowadays they're used as the same thing. Okay, have a question?
Yeah, can you explain that last requirement, that theta I of y I is t?
So this is just basically, I want y0 to be equal to the first part of boundary I selected. and then the second one to the second. So y1 to be the second part of the boundary estimate.
But what does it have to do with theta 1 and theta 2? I mean, you could just say y0 is literally dx0 and y2 is literally
They have an orientation. So
yeah.
I embed them in a certain way.
Yeah.
So I embed this maybe this way and then this one the other way around.
Yes, but it's just theta I is a map from yi times an interval. What does it mean when you apply it to yi?
Well, I mean, so looking at it as a manifold, this will give this without the orientation. It has to match exactly, but it just puts an orientation to it. So here there's a positive orientation, and then here there's a reverse orientation to that. So that's the only thing. But they have to match. If you know, like without considering the orientation, they have to be the same. Okay. Now that we know what a Bordism is, we can now write the axioms of a TQFT. Okay, perhaps I get another check. So these axioms were defined by Attia in his 88 paper called Topological Quantum Field Theories. Okay, so here are the axioms. A TQFT in D dimensions over a ground ring, let's say ring R, consists of the following data. Of the following. So there's two data needed. So the first of all is we need a finitely generated R module Z sigma associated to each closed smooth manifold, smooth d-dimensional manifold sigma. So that's one thing. And then we need an element. This chalk is very hard to write, so I'm an element Zm, which will be an element of the model associated to its boundary, associated to each smooth manifold d plus 1 dimensions. Okay, fair enough. And then such that here comes the axioms. There are two of them. Z is functorial with respect to orientation preserving diffeomorphisms of both sigma and m. Second of all, we need Z to be involuntary, and that is just these parentheses are just useless. So this, okay, this is just orientation reversing, and then this will be our dual model, because as this is a model, this will be the dual model, and then this is just orientation reversing. And then we need, the third axiom is we need Z to be multiplicative.
So what do you mean when you write Zm as an element of Z?
Okay, this is dimensional manifold M. So here we have sigmas. They're of D dimension,
Okay.
and then there are M's which are one more dimensional.
Okay.
And then we say, so if we have, for example, if this is your M,
Okay.
and then this will be its boundary. This is of D dimension, right? So we know that there is an R model associated to this guy.
Okay.
And then we're saying, okay, for every M that has this property,
Oh, I see.
we assign M an element of this module.
Oh, okay.
So it's kind of, I see it as reversing the dimension, because here M is bigger, but here it's just an element of the
So
module.
Z of M is an element, and Z of boundary M is a module.
Sorry?
Z of boundary M is a module, and
Yes,
Z of
and
M
then
is
this is
an
an
element.
element,
Okay.
exactly. So what this means basically is, so then we will have, so the TKFTs are of this type. It's the way you assign these. So they will, so the models here will have elements. So if you have boundaries, the elements will exactly correspond to all the ways that you can stick, like, so this will be one, and then like this will be another one, and then all of the manifolds that you can stick to those boundaries, basically. So they will give you exactly those. Okay. One point that is important is, well, even though it's not explicitly written here, this actually defines a functor. And in the most general form, we can say this. So we actually have Bordisms, which we learned, which are of these type. So here, this X is a Bordism. So in all the literature, it was called a cobordism between Y0 and Y1. So we have Bordisms of dimension D and D plus 1. And then we assign them to modules in which physicists usually take vector spaces over complex numbers. And then the TQFT is a functor, as it's a way of assigning vector spaces to these Bordisms. Oh, yes?
I think you didn't finish the third part. What is Z multiplicative with respect to?
Good question. I finished it. I will explain what they mean right now, in just a second. But just before that, I want to emphasize that TQFT is this functor here. So what physicists study as TQFTs is what mathematicians take as a functor. Okay, lovely. And then, so we can say, we can talk about the physical interpretation of this axioms. Meaning of these axioms. So, first of all, the first of them, it's actually intuitive. So if you have f that goes from sigma to sigma prime, say, and then this is an orientation preserving diffeomorphism, then we have z of f that takes this module here, and then this is an isomorphism. Okay, nice. So, and then we can say the meaning of 2 is, again, very clear. This just means reversing the orientation means moving to the dual module. But now the third one is a bit longer, so we can discuss that now. So, first of all, we need, if we have the union of two manifolds, we want this relation in the modules. So it's a tensor product of the modules associated to them. So now this will have some consequences. So first of all, let's assume take delta M1 to be, for example, sigma 1 union sigma 3, and then delta M2 to be sigma 2 and sigma 3 in the other orientation. Then we can, so we have this, and then we have this, and then whoop, and then they stick to each other because they have different orientation, right? So we can say, okay, let's see what happens if you look at M, which will be they're gluing through sigma 3. And what will happen is element stick to this will be the natural pairing of these two elements in the two modules. And there will be a function going, so because of this, we can write this as, so M1 I can often know as tensor product of sigma 1 and then sigma 3, and then I have this tensor product of it with its dual module, right? Because the orientation reversing just becomes the dual module in the module category, and then we have the sigma 2, and then this will have to map to, because of M, this guy over here. Now, we're still not done with the third one. A few more remarks here. So suppose, okay, so suppose we have this. So suppose we write it upwards. Suppose we have delta M to be the sigma 0 and sigma 1. So we split into two. We can do that. It's not forbidden. And then we say, let's look at the other, so take the direction of this one, reverse this one. Okay. So it doesn't matter if one of them are empty. It can be. No constraints. So then Zm will be an element of this, but then this is just this at home between sigma 1 and modules of sigma 1 and sigma 2. Cool. So if we have here.
I guess in this discussion you take your ring R to be a complex number.
Sorry?
You have some ring R. In this case, it is just the ring of complex numbers. Yes.
So I do not necessarily have to take them complex numbers, but usually I take them complex numbers. So I'm giving examples, kind of explaining them through them.
But then, if it's not the complex numbers, then there's no quality.
Well,
there's only a morphism from M dual tensor N to the homomorphisms from M to N.
I know you can, well, instead of taking complex numbers or real numbers, you can take other rings, and then you can still build the same structure. It will be slightly different, but you will, so in analogy to this, you will still have the same kind of properties that makes, but I haven't studied those kind of stuff. So we're now going through everything, but kind of assuming it's a nice ring that we can work on. But anyways, so remark. We are almost there in the most interesting part. So, one of the remarks we have to give is if sigma, wrote very bad. If sigma is the empty set, then we force the model associated to it to be the ring itself. And then if we look at the empty set as M, so this is of D plus 1 dimension, so there's no actually, so there's no bordism you can stick between two boundaries, then we still have to associate it to some element. And then we force this to be the unit element of the ring, 1. So that's the first remark. And then the second remark we have to do is we can take M to be sigma times I, where I is the unit interval. So we have just whatever sigma is. This is the sigma, and then we just like make it a cylinder to that. So that now this will be our M. So this is, looking at this, is just an endomorphism of the model associated to sigma. Right? Okay, nice. So this is the meaning of the axioms, and then still we haven't like giving them physical meanings. So maybe just a little briefly physical meanings of these. So physicists think of sigma here as the physical space. And they usually take this, sigma plus I, to be the, well, this over here is just imaginary time added to it. And then the module associated to sigma will be the Hilbert space. Again, we're doing mathematics, but just to tell physicists, if there are any physicists here, I think there are some, but to give them a motivation to listen to the rest of the talk. So this is the Hilbert space of the theory, of the quantum theory, and very precisely. And if delta M equals sigma, then this guy is a vector in the Hilbert space, right? So what is thought of M is it's the vacuum state. But again, this is just physical part of the talk. And so for closed manifold M, this will be a number. Because it's closed, it will have no boundary, so this will just be the ring. So this is a number, and then this number is the vacuum expectation value. And in statistical physics, they call this the partition function. I will not explain how this is actually the partition function and stuff because it's not a physics talk, but for the motivation behind it, that's how they're all related. And now to the most fun part, let me see how I do this. Okay, I will raise some of axioms. But keep these in mind, they'll be useful. So now we're the last part. I know this time we started a little bit late, so sorry for but only last 10 minutes I think. We're gonna take the Ising model and then express it as a TQFT, which will be fun. Okay, so in this sense, what Ising model will be, it's a functor from Bordisms of 1 to 2 dimensions. So we're actually working with the 1 dimension as well. But anyway, so, and then we're looking at the lattice Bordisms. And by lattice Bordisms, we just mean we take this and then stick a lattice on it. Very straightforward. And then it goes to vector spaces over C. Surprising. So now, as this is a functor, we can say, okay, we know the objects and morphisms of these precisely, and now, so the objects are 1-dimensional lattice manifolds, and the morphisms are 2-dimensional lattice manifolds between those 1-dimensional lattice manifolds. And then we can say, okay, but which types of vector spaces will these go to? And then we can say, okay, let's look. Objects. So ISP will be, so we have, this is a 1-dimensional manifold, this is the lattice stick to it, just an object of this one. This will go to map between the configuration space and complex numbers. And the morphisms will be, it was 2-dimensional lattice Bordisms here. So now they were of the form of this. This is before, with the big parentheses. So they were going through S0, A0, 2, S1, pi 1. So this was actually giving the correspondence between, so we had, let me draw it here. I can draw a lattice on this one, that'll be easier. So we have a lattice stick here, whatever, and then the, and then this is also lattice, so these are assumed the vertices. So it takes one and then makes go to the other one. So we can write this. So this is the configuration space for this blue one over here. Maybe write it in blue. And then,
Sorry, what were Y and gamma again?
so Y and gamma is a 2-dimensional, so Y is a 2-dimensional manifold here, and then gamma is a lattice stick to it. So these all come in pairs. The first one is the manifold, and the second one is the lattice stick to it. So we can say if we only be projected to this part, we will have configuration space of this guy over here. And then if we project it to the other side, this part, we will have the configuration space of S1 and P1. But they're actually all contained in this guy over here, which is the big manifold, right? So nice. So this is the parentheses part.
So S0 and S1 are parts of the boundary of Y.
Yes. So maybe I can write it here. So this is S0 pi 0 over here. And then this is S1 pi 1. And then this blue thing, so this itself is the manifold Y. And then gamma is the lattice stick to it. And then this is the configuration space over the big thing. And then these are the configuration spaces over the little ones. So it actually, if these are to interact, they run through all of this. Okay, now we know what the morphisms, what the structure was here. So if we look at what I will carry Y gamma to, this will actually be, so this is a little bit of category theory terminology, which I don't have time to explain. But if you look at the category theory book, I think it'll be fine. So this is the the push forward of this, and then this is the pullback of this. So what we do is we go through this back here somehow. We go through this, which is K. I will add what K is explicitly in a second. And then we move back to this one after going through the big levels. So this is a function between this two. Okay. So these are just the objects, the functor carried to the vector spaces. Okay, and then what K is, you can ask me and I will tell you. K here is, well, I can give you the configurations. These are configurations, right? So for the K configuration, this will be the product over all edges of this weighting function of G of S E. Okay, yes. So what it does is actually, so it counts through all the inside values, all the possible inside values, while going from this to that one. So, maybe erasing that part, just 5 minutes left. So if we take y gamma to be 0, 1 times this one-dimensional lattice manifold here, and then we take it and then we make it longer, like a cylinder, then the resulting endomorphism of IS pi. Now how can I say this sentence is, it's because I know if this is the case, you know, if this is the case, oh here, if this is the case, then this will just be an endomorphism of the model associated to the boundary. So if I have one kind of, I have this one-dimensional lattice thing, but this is a one-dimensional Ising model, nice and sweet, and then I carry it outwards. Not the best drawing in the world, but I think it's understandable. Anyway, so this is my YG. Then I say that this thing that goes over here is an endomorphism of this the model associated to this one-dimensional system, and then this will what our transfer matrix will be. Right, because this is a vector space, and so we're looking at the endomorphisms of vector space, which will be a matrix. We can write it as a matrix, and that will exactly be the transfer matrix of this system here, this yellow system. Okay, so all this story was basically for expressing this very physical lattice spins interacting system, and then writing in somewhat more algebraic way. So it's easier to work on. It's nice. Just two sentences. The example I gave is a very simple one. It's you might think, okay, but then we can already solve this. Why are we doing all this stuff? Like, why do we put that much effort to this? But approaching classical split systems this way allows us to generalize it. So we see. So here we can change the group. We can change the weighting maybe, and then changing this. So this is in this case abelian. If you don't make it abelian, you'll have tons of problems trying to write if you try to write transfer matrix and stuff. So you can take the classical spin system and you might not be able to write the transfer matrix. But if you express it as a TQFT, then you have more tools to approach it. So it's useful. So this is the most basic example again I gave, but they're widely used. And I think so Dan Fried has his slides on the internet online, and then he explains why this is very important and how it's used more precisely. He is the expert, I know. But I try to give the intuition behind it, so if anyone has questions, I can answer. Yes?
So the functor is not a contravariant, the TQFT.
Sorry?
So the TQFT functor is not contravariant, or it's the TQF.
Yes, here?
Right,
Okay.
is it contravariant or is it covariant? Because I think the usual language says it's a covariant functor from coordinators
Uh-huh.
to vector spaces, sure.
Even-
But like you're using ordinators, so it should be contravariant.
So okay, even though I've studied category quite a
Yeah,
bit,
sorry,
I
like-
still confuse those two
Yeah,
terminology,
yeah,
but
sorry.
it
Contravariant
doesn't
is
change the
inverse
direction if
of
you're asking that. No, I don't think so.
So this Bordism
if I'm not mistaken.
corresponds to the usual like coordinate.
Sorry?
So the Bordism you're using actually means coordinate.
Yes, yes. That's what I tried here. Because there's a bit of misusage of the words. So here, so some people, so Atiyah refers to what I say Bordism as a co-Bordism, but then Fried uses it Bordism, and then like some of the authors, the more recent ones say it's a Bordism, the older ones usually say it's a co-Bordism. But it's this is what I take as Bordism, and yeah, Atiyah tells this is a co-Bordism one. Yes.
Right. So in the Bordisms, the objects are like the manifolds with boundaries, and the boundaries are like under the up to diffeomorphisms of like.
So the objects
summary
here
representations.
are the d-dimensional manifolds, and then the morphisms are the one upper dimensional manifolds that you can stuck between them, which will be their Bordisms. So you have to stick them nicely to the boundaries. So the objects are here red, and then Bordism is blue.
Sure. So it's not up to like orientation preserving. Where does that?
Sorry?
So from what I read, so I thought the objects are deep manifolds up to orientation preserving diffeomorphisms attached with like d plus one.
No, the objects itself are the one like d+1 dimensional manifolds. So, sorry, morphisms are those, and then the objects are just like manifolds of formless dimension. You have a question?
Yeah,
Okay.
it's a bit of a broad question, but so you said these axioms of Atiyah are supposed to axiomatize topological quantum field theories.
Yes.
But in that sense, what exactly, or like what approximately do we even want to understand by what's a topological quantum field theory? Well, I mean, formally, we just axiomatize it like this, but what is what do we want this axiomatic system to give us if it's
Well, okay. I'm not a physicist, so I don't know the physical side of the story that much. But as far as I've seen, it's to generalize and then make them all the same type, because physicists they have all these different types of different. So it's probably to generalize, but I'm not an expert in this. And then maybe one little remark, as I remember now. So Atiyah's axioms uses like it literally uses Bordisms and like manifolds and orientation and everything, but this is not the only way too. So there is even a more general approach to TQFTs that's axiomatic, and that's explained in Thrive's book. So he has a book, not invariance through three dimension in TQFTs, and invariance of three-dimensional manifolds, I think that's the name of it. If you search a plane, it probably pop up. So in that case, he even goes into more detail and says like, it does not have to be orientation, it just has to be some space structure, and then he explains what the space structure is, and then he says that you can build the whole stir differently. But physically, this is what's usually used. So, and then the most, I think, intuitive one.
Then more concretely, if you just consider the classical easing model, can you point what exactly makes it a field theory? Like, what exactly is the TQFT aspects of the easing model? Is it just the way that it takes some states and outputs some numbers? Is that what it means to be field theory?
I don't think I can answer this question and satisfy you because I don't know that much physics. But
I think-
Professor Wen, do you have an answer to this question?
No, I think field theory is if you had like there's some cases where instead of a lattice you somehow approximated as if you get to this.
So if you're asking what physically makes something a field theory is, I don't know the answer to that. Okay, so I don't know like the holy axioms for a theory to be a field theory, but there probably is. But this is like to make it sit on some mathematical structures. Because physicists, they just go around like saying, oh, we'll call this a QFT. This is the mathematical background behind it. You can take any of them and then write it with these structures, which is useful at the end of the day. Okay, so if any other questions? If not, thank you for listening.